Hello. Today, we're going to explore one of the most fundamental equations in physics and engineering, the heat equation. By the end of this video, you will be able to understand what the heat equation describes and how it's derived from basic physical principles. Essentially, the heat equation is a mathematical model that tells us how temperature changes over time and space within an object. It's a powerful tool for predicting how heat will flow. Think of it this way. If you have a hot object next to a cold object, the heat equation can predict how the temperature will equalize over time. It describes the process of thermal diffusion. So our main goal is to understand this equation and see where it comes from. To derive the heat equation, we need two key physical principles. Let's start with the first one. The first principle is the law of conservation of energy. This law states that energy cannot be created or destroyed. In the context of heat, this means that any change in the internal energy of a system must be due to heat flowing into or out of that system. We can write this as an equation. The rate of change of internal energy, which we'll call E, is equal to the net rate of heat flow into the system, which we'll call Q. Now, how is internal energy related to temperature? For a simple material, the change in internal energy is proportional to the change in temperature. The constant of proportionality is the specific heat capacity, C, which tells us how much energy is needed to raise the temperature of a unit mass by 1 degree. So, the rate of change of energy is C times the mass, m times the rate of change of temperature, T. Combining these, we get our first piece of the puzzle. The rate of temperature change is directly related to the net heat flow. This equation tells us that if more heat flows into a system than out, its temperature will increase. If more flows out than in, its temperature will decrease. This is a direct consequence of energy conservation. Now for the second principle, how does heat actually flow? This is described by Fourier's law of heat conduction. Fourier's law of heat conduction tells us that heat flows from hotter regions to colder regions, and the rate of flow is proportional to the temperature difference. Imagine a metal bar. If one end is hot and the other is cold, heat will flow along the bar. Fourier's law quantifies this. The law states that the heat flux, which is the rate of heat flow per unit area, is equal to a constant, K, times the negative of the temperature gradient. The constant, K, is the thermal conductivity of the material. Let's break that down. The temperature gradient is just the rate at which temperature changes with distance. The negative sign is crucial. It means heat flows in the direction of decreasing temperature. In other words, heat flows downhill on the temperature landscape. So if the temperature is increasing as you move to the right, the gradient is positive, and the heat flux is negative, meaning heat flows to the left. This is exactly what we expect. Heat flows from hot to cold. So to recap, we have two principles. Energy conservation tells us that temperature changes are caused by net heat flow, and Fourier's law tells us how that heat flow is driven by temperature differences. Now we're ready to put it all together. Let's consider a small, one-dimensional slice of material, like a thin section of our metal bar. We'll call this slice dx, thick. Heat can flow into it from the left side and out of it from the right side. First, let's apply the conservation of energy. The rate of change of internal energy in this slice is equal to the rate of heat flowing in minus the rate of heat flowing out. The rate of heat flow is the heat flux, Q, times the cross-sectional area, A. So, the rate of change of energy is A times the heat flux at x minus A times the heat flux at x plus dx. Now, let's use our other expression for the rate of change of energy. C times mass times d T dt. The mass of our slice is its density, rho, times its volume, which is A times dx. So we have rho times C times A times dx times d T dt. We can divide both sides by A and rearrange the right side. This gives us rho times C times dx times dt dt equals the negative of the change in heat flux over the distance, dx. Now, let's divide by dx. As dx gets infinitesimally small, the term on the right becomes the definition of a derivative. So, we get ρho times C times the partial derivative of t with respect to t equals the negative of the partial derivative of q with respect to x. This is our conservation of energy equation in differential form. We're almost there. We have an equation that relates the rate of temperature change to the rate of change of heat flux. but we want an equation that only involves temperature. This is where Fourier's law comes in. We'll substitute our expression for heat flux, Q, into the equation we just derived. Remember, Fourier's law states that Q equals negative K times dt dx. Substituting this into our conservation of energy equation, we get rho times C times dt dt equals the negative of the derivative of negative K times dt dx. The two negative signs cancel out, and if we assume the thermal conductivity, K, is constant, we can pull it out of the derivative. This gives us rho times C times d t d t t t equals K times the second derivative of t with respect to x. This is the one-dimensional heat equation. Let's rearrange it slightly. To a more standard form, we can divide by rho times c to get dt dt equals K over ratio c times the second derivative of t with respect to x. The term K over rho c is so common that it's given its own name. It's called the thermal diffusivity, and it's represented by the Greek letter alpha squared. It tells us how quickly temperature changes diffuse through a material. A high alpha squared means fast diffusion. So the final form of the one-dimensional heat equation is d t equals alpha squared times the second derivative of t with respect to x. This elegant equation describes how temperature evolves in a one-dimensional object. We've derived the one-dimensional heat equation. But what if heat can flow in 2 or 3 dimensions? The derivation is very similar, but the math gets a bit more involved. The key is to replace the second derivative with a more general operator called the Laplacian. In 2 dimensions, the Laplacian of t is the second derivative with respect to x plus the second derivative with respect to y. In 3 dimensions, we add the second derivative with respect to z. Using this operator, we can write the general heat equation in a very compact form. The general heat equation is dt dt equals alpha squared times the Laplacian of t. This single equation describes how temperature changes in any number of dimensions. Let's visualize what this means. The Laplacian of t is a measure of how much the temperature at a point differs from the average temperature of its neighbors. If the Laplacian is positive, the point is colder than its surroundings, so heat flows in and its temperature increases. If the Laplacian is negative, the point is hotter than its surroundings, so heat flows out and its temperature decreases. This is the mathematical expression of heat flows from hot to cold. So, we've seen the heat equation and where it comes from. But what can we do with it? The heat equation is a partial differential equation, or PDE, and solving it can be quite complex. To find a unique solution, we need to specify 2 things: the initial temperature distribution and the boundary conditions. The initial condition tells us the temperature at every point in the object at the very beginning at time t equals 0. The boundary conditions tell us what's happening at the edges of the object. For example, is the boundary held at a constant temperature, or is it perfectly insulated? Let's look at a classic example. A metal rod of length L, initially at a uniform temperature T_initial, whose ends are suddenly plunged into ice water at 0 degrees Celsius. The initial condition is that the temperature is T_initial everywhere. The boundary conditions are that the temperature at both ends, x equals 0 and x equals L, is held at 0 degrees for all time. The solution to this problem describes how the temperature profile in the rod changes over time. It's a beautiful example of how a complex physical process can be described by a relatively simple mathematical equation. The solution shows that the temperature in the rod will decrease over time, with the cooling happening fastest near the ends. Eventually, the entire rod will reach the temperature of the ice water, 0 degrees Celsius. Let's quickly recap what we've learned today. We started by understanding that the heat equation describes how temperature changes over time and space due to heat diffusion. We then derived it from 2 fundamental physical laws, the conservation of energy and Fourier's law of heat conduction. We saw the one-dimensional form, dt dt equals alpha squared times the second derivative of t with respect to x, and the general form using the Laplacian operator. Finally, we discussed how to solve the equation by specifying initial and boundary conditions, and we looked at a classic example of a cooling rod. The heat equation is a cornerstone of mathematical physics, with applications ranging from designing computer chips to understanding climate change. I hope this introduction has given you a solid foundation for further study. Thank you for watching.